In hopes of returning home, Dorothy and Trout start out on an adventure to seek help from the all-powerful Wizard of Oz. On the way, they meet the Scarecrow, the Tin Man, and the Cowardly Lion. While the Scarecrow believes he doesn't have a brain, he is really lacking experience, since he is only 2 days old. However, what he fears the most is fire, because straw is very flammable. In our next experiment, Blakely Tresca creates a chemical volcano, which would really have the Scarecrow dancing in fear. It's a good thing there are no volcanoes in the Land of Oz. The Tin Man thinks he's missing a heart because he can't hear it beating. But kindness towards others is the true measure of someone's heart. How sturdy is his tin body? How could we make it stronger? And does it really rust without oil? Deb Coates explores the properties of metals in our next set of experiments. The Cowardly Lion is scared of the unknown, like many of us are. The more things we learn about and challenges we face help us grow in our confidence and abilities. In our next set of experiments, Carl Stachew and Matt Barringer explore the pressure created from gas with explosions big and small. Once we know the science behind what is happening, there is nothing to fear.
Welcome everyone, I'm Carl Stachew. Today I'm going to show you how to make the Cowardly Lion overcome his fear of noise. And how I'm going to do that is I'm going to take this gallon of water and use it to crush this 55-gallon drum. So first I need to add the water to the drum. I'll do that now. So this is an empty drum. And then I'm going to place this drum on the propane heater. And then what happens when you heat water? Eventually it boils. So that liquid is actually going to turn to water vapor, which we'll see in about 10 minutes. And I'm going to leave the top open. So let's get rid of these tools for now. So I'm going to put this drum up on top of the heater, and then we'll see in about 10 minutes. So I'm going to use this hose to add some water to the top of the drum, and I use that as an indicator to tell me that this drum is sufficiently hot, which means I've boiled enough water out of that drum to go ahead and close that lid. And it's going to take about 10 to 15 minutes to heat it up. You'll see the water vapor is going to come spewing out of here. You'll see some water vapor coming off the top. Then I'm going to seal it back up, and then we'll start cooling it with a hose and see what happens. So it's a little hard to see, but you can start to see water vapor coming out of the outlet of this drum. Okay, we've heated the drum now for roughly 15 minutes, and as I said, as you heat water, it's going to boil. You see the water vapor now coming off the top of the drum. At home, when you're boiling water in a pot, you see that water vapor leaving the surface of the water in your pot. Now I'm going to go ahead and seal this. And what that's going to do, it's going to actually build a little pressure. So the water's still boiling, but now it's got nowhere to go. We've closed the vent. And one thing you'll notice, I've got safety glasses on, I've got gloves, towels. This drum is hot. So important to protect your eyes and your hands with this demonstration, because we are working with boiling water. And with that, that's usually a sign when it does a little pinging noise. Now we're going to set it down, and we're going to turn on the water hose, and we'll start cooling that drum. So as I cool the water vapor, it's going to condense. So I filled this drum with hot water vapor, and now I'm cooling that vapor back down. And remember, we started with a 1-gallon plastic container of water. And this drum here is about 40 to 55 gallons. And that'll become important later. And so if you ever worked with your parents or grandparents, they might tell you to grab the persuader. So we're going to try and persuade this drum to collapse with a little tap of the hammer. And there you go. Now, watch what happens when I open up the lid. So I've got my microphone right down by the lid. This can vary, but sometimes you'll hear the air actually rushing into the drum. So what did we do there? Remember, we started with a gallon of water. Okay, look at the volume difference. Took that water, heated it up to boiling, filled the empty part of the drum with boiling water. And as I mentioned, when I cooled it, it's going to condense. So it's going to go from a water vapor back to a liquid. And it's actually going to be a little bit less volume than this container because we actually boiled some of the water out of the drum. And so when we do that, we reduce the pressure inside the drum. We create what's called a vacuum. And so the pressure inside the drum is significantly less than the air pressure outside. So air pressure is not really something we feel, but the closest thing I could think of is if you're in the deep end of a pool and you start feeling your eardrums getting ready to pop, that's water pressure, but it's pressure. You can feel it pressing against you. And that's what happened with this drum. So, you might say, yeah, but you hit it with a hammer. And so as much as I'd like to think I have the power of Thor, the god of thunder, I'm going to take an empty drum here, and let's see if I can cause it to collapse just by hitting it. Okay, I barely touched that drum and it collapsed. So the work was actually done by the outside air pressure pressing against the walls of that drum. And so now that we know what happened, why we have that large bang, that collapse, that's the steel finally giving way. Now we've explained the science behind how a gallon of water can crush a 55-gallon drum, creating a large noise. And now that the Cowardly Lion understands the science behind what we did today, he no longer has to be afraid of that loud noise. Thank you for joining us. Have a good day.
Hi everyone, my name's Matt and I'm here to talk a little bit about acid-base chemistry today. So, what are acids and bases? Acids or bases are things that we use all the time in chemistry. Some of them can harm you, and those are the strong acids and bases, and we let the professionals deal with those. Some of them are fairly harmless, such as vinegar, baking soda, or Alka-Seltzer, and are probably present in your home. Today, we're going to use Alka-Seltzer. So what's the big deal? Why are acids and bases so cool? Well, acids and bases, when mixed together, perform a chemical reaction that always produce a gas, a salt, and water. So when these reactions take place, it's a very, very fast reaction, and it can often give you fizzing or bubbling, which looks pretty cool. But other than looking cool, acid-base chemistry can do things like launching rockets, which we'll see today. Now, you may have seen Alka-Seltzer used before, either by yourself or someone at home when you've had an upset tummy. So Alka-Seltzer contains sodium bicarbonate and citric acid, which are our acid and our base, and are the two ingredients we're going to use to do the acid-base reaction in this experiment. Now, when you perform these experiments, make sure you wear eye protection, or even if you have gloves, wear gloves. So what you'll need for this experiment is one film canister, a pack of Alka-Seltzer. In this demo, we use a tube to help launch the rocket. It's not required, but recommended, and some water. The first thing you'll do is put your Alka-Seltzer tablets in the film canister. Now here we have 3 different experiments set up, each with a different amount of Alka-Seltzer. With acid-base chemistry, the more acid and base you have, the more gas you'll produce and the bigger your reaction will be. So here, in each of these, we have a half of an Alka-Seltzer tablet, one full Alka-Seltzer tablet, and 1.5 Alka-Seltzer tablets. We're going to perform the experiment with all three and see what happens. So after you have your Alka-Seltzer in each of the film canisters, the next thing you'll do is use some water. Now, as I said before, these reactions go very fast. So once you add the water, you'll need to move a little quickly. The help of an adult always helps. So for the first one, we'll test the half of Alka-Seltzer tablet. We'll pour in some water, and you can see that it's already starting to fizz. Put the cap on and drop it into our tube. So you can see we had a gas buildup in the film canister, and it popped out just on the outside of the tube. So now, for experiment 2, we'll move to the film canister with one Alka-Seltzer tablet. What do you think will happen? Let's find out. Again, we'll pour some water into the tube, place our top on, and drop it in. And that one, you can see, went a lot further up. So again, we had more Alka-Seltzer in there. You can look in your tube and see all of the fizzing and bubbling that we mentioned before. So now we'll try the third one. As a reminder, the third one has 1.5 Alka-Seltzer tablets. We've seen a half of Alka-Seltzer tablet that just went above the tube. We had a full Alka-Seltzer tablet that went a bit higher. What do we think will happen with 1.5 Alka-Seltzer tablets? Let's find out. We'll pour in our water, put on our top, drop it in our tube. And that one looks like it went a little bit higher yet. Again, we can see the fizzing in there. There's a bit more in this tube than there are in the other tubes. And that is because we had more acid-base chemistry going on inside the canister. So what did we learn today? We learned a little bit more about acids and bases, and although some of them can be dangerous, some of them we can find right in our kitchens or right in our houses. We learned that acids and bases, when mixed together, produce gas. And depending on how much acids and base we have, the amount of gas that's produced, judging by how high the rockets went. Finally, we learned that the chemical reaction behind acid-base chemistry can do cool things like launching rockets. So I hope you had fun today and hope to see you soon. Thanks.
So this is a chemical reaction that will produce a volcano. This is an ammonium dichromate. And once I ignite this, the heat of the ammonium dichromate reacting will be enough to cause the rest of the reaction to ignite, and it'll be a self-sustaining reaction, and it'll be a nice volcano with fire and sparks. And I'm going to add some ethanol as a fuel just to get it started. Now the color has changed, but all of the material that we started with has remained in this volcano.
Hi, I'm Deborah Coates. I'm here to talk to you about metals. So we have to start with a definition. What is a metal? So a metal is something that's naturally occurring, and it is durable, hard, shiny, dark in color, conducts electricity, is malleable, which means it's flexible, and easily fusible, which means it can easily be joined with another piece of metal or welded or soldered. This is an example of metal. See, it flexes, looks like what you would expect when you look at a metal, and this is a piece of sheet metal that's used in construction. But as we look here on the table, one of the things we can see is there's lots of other things that may or may not be metal. So we want to talk about minerals. So minerals can either be metallic or non-metallic. And when we look at those minerals, we can look at them and say, okay, does it look like a metal or not? So the definition of metal is it's got to be dark and shiny. Well, this is certainly dark and shiny, but it doesn't look like a metal. This is a piece of tourmaline. This is also a piece of tourmaline. Doesn't look anything like a metal, but it's dark but it is shiny. This is a piece of watermelon tourmaline, and you can see why it's called watermelon tourmaline. It's got the green and then the pink and the green again, just like you'd cut into a fresh slice of watermelon. But other things on my table definitely look like minerals or metals. This is a mineral called iron pyrite or pyrite, and it came out of the ground. No one cut this in this shape. This is a crystal of iron pyrite. Many minerals will make crystals. This is a crystal or a collection of crystals of the mineral called galena. It's a lead ore, and it's a crystal of galena. So when we think about metals and what they sound like. So for example, there are some metals that come out right out of the ground and look exactly what we think about them. Copper is one example. When we talk about copper, copper comes out of the ground like this. This is a piece of native Michigan copper. We've sliced open so that we can see what the inside looks like. If you were to pound that flat and mint it and put some imprints on it, you'd make pennies. Silver comes out of the ground and is mined as a single substance. It can be pounded flat and turned into coins. Same with gold. It can be mined, pounded flat, and turned into a number of things, coins and jewelry and artwork. But not everything that comes out of the ground is good for building things. Gold, silver, and copper are far too soft. So we look for ores of other stronger metals like iron, and this is an iron ore. So this mineral is called magnetite. This is an iron ore, or it's an ore of iron, so we mine this to get the iron out. But the really neat thing about this particular mineral and this particular sample, it's a lodestone. It's a natural metal. So we know that a magnet will stick to things that are made of iron. It certainly sticks to this. It'll stick to my sheet metal, but it won't stick to my iron pyrite. So this particular mineral is called a lodestone. It's so naturally magnetic that even paper clips and small magnets will stick to my sample. We have one other thing on here that's kind of in between. This is a piece of silicon. Not silica, which is what glass is made out of, the building block of glass, not silicone like you would have on your kitchen baking mats, but silicon. And this is in between. It has some properties of a metal and it has some properties of nonmetals. One of the properties that it's valued for is that it kind of conducts electricity, or it is a semiconductor. So if you were to slice this very, very thin and imprint a computer chip, you'd find this in your microprocessors for your home computers. So one of the things that we wanted to talk about this Tin Man is rusting. We want to help the Tin Man avoid rusting. So rusting is just a fancy word for oxidation, or a word we use for oxidation. And oxidation means that Oxygen combines with a metal. We're probably most familiar with oxidation through by rusting, that dark red rust color that happens on metal implements or your car. But other minerals will oxidize. They may or may not look exactly like rust. For example, copper oxidizes in this beautiful green color. You can see even my piece that we dug out of the ground has some oxidation taking place. This beautiful green patina is found on a statue in the New York Harbor called the Statue of Liberty. That beautiful green of the Statue of Liberty wasn't always like that. At one point, it was a dark copper color because the Statue of Liberty is made of sheets and sheets of copper that are no thicker than 2 pennies thick. And over time, it's turned into that beautiful statue that we know as the Statue of Liberty, that beautiful green color. So we want to prevent oxidation. And one of the ways that we can experiment at home with oxidation, looking at oxidation, is to take some pennies and put them in a small beaker and put some household vinegar on them. Let them sit overnight. When they sit overnight, what you'll find is they come out and they're much cleaner and much shinier than they would. What you've done is remove that oxidation. For the Tin Man, we want to prevent oxidation, and so as long as we coat the Tin Man with some barrier, he won't oxidize. He won't rust. There's a few other places you can look for oxidation or an oxidation experiment. One is you've probably experienced this when you cut up an apple and you don't eat it right away. It'll turn brown. That's oxidation. The apple is reacting with the oxygen in the atmosphere and turning brown. But if you coat it with a little bit of vinegar or lemon juice or something else acidic, it'll prevent that oxidation because you've put a barrier down between the apple and the atmosphere, and that prevents browning. For our Tin Man friend, he was trying to reduce rusting and reduce oxidation. And so as long as our Tin Man has some kind of coating on his tin to prevent rusting or oxidation, he will live a good long time.
Dorothy, Trout, and her friends are within sight of the Emerald City, where they hope to find the wizard. As they start to cross the field of poppies, an odd mist appears, and they drift off to sleep.